So let's do a couple of examples. Let's form a polynomial whose zeros and degree are given. So if I have a polynomial with these zeros, that means I have a function that has the factors of x plus 2, x minus 0, and x minus 4. Well, obviously, since that x minus 0 is simply just x, I can pull that x out in front. Now, it also says it has to have a degree of 3. Well, this already has a degree of 3. Since this x is to the first power, this x is to the first power, and this x is to the first power, that has a total degree of 3. If I multiplied and FOILed all of this out, I ultimately would have an x to the third power as my first term. What if I have a polynomial that has zeros at -2, but it has a multiplicity of 3. So that means it has a multiplicity of 3. It also has a 0 at 1 and at 2. If the total degree is 5, I have that because I have 3 x's here, 1 more plus 1 more makes a total degree of 5. What if we graphed a polynomial using its x-intercepts? So here we have a polynomial f of x is equal to x squared times x minus 2. First, if we want to find the x and y intercepts, recall how we did this in previous sections. To find the x-intercept, we set y equal to 0. So we're going to set this whole side equal to 0. Using the zero product property, when two things multiply to each other equals 0, that means either the first part or the second part must be 0. If the first part is equal to 0, that means x is simply just 0. If the second part is 0, that means x must be 2. So I have two x-intercepts, one at 0 and one at -2. To find the y-intercepts, I set x equal to 0. So y equals 0 squared times 0 minus 2. 0 times -2 is simply 0. So y equals 0. Now, if we use the x-intercepts to divide the x-axis into intervals, what we're going to do is we're going to just draw the x-axis for now. Of course, there's a y-axis that runs through here, and I mean, if we wanted to draw it, we could. This would be the y-axis, but we don't have to do that. This y-axis would mean this is 0, and we also need the numbers 2. We're dividing this x-axis into these intervals. We want to show 0 and we want to show 2 on our x-axis. So we're basically dividing this into different intervals. There are 3 intervals. We have the interval from 0 all the way to -infinity. We have the interval in between 0 and 2, and then we have the interval between 2 to +infinity. So we're going to test all of these intervals to test to see what the graph is doing. I basically want to know, since my graph is going to hit these points, I know these are x-intercepts without a doubt. Is my graph going to come down and come back up? Is it going to come up and come back down? Maybe it's going to touch and come back down and go up. I don't know. All I know is that it's going to touch or cross through these x-intercepts. What I'm looking to find is what the graph is doing in these intervals. Is it above or is it below? So I know the direction in which it's approaching that 0. So we're going to find what's called a test point, okay? In the next section down here, we're going to test points in each of these sections. Pick any number in each of these 3 intervals to find additional points to see if the function is above or below the x-axis. So I'm going to pick just some random test points. For example, in this range right here, since this is 0, I'm going to pick the number -1. So I'm going to pick a number -1 over here. and I'm going to test it. I'm going to plug that -1 into the function. So if we go back up here into the function, all I really care about is whether it's positive or negative. I don't necessarily care too much about what the value actually is. So if I plug -1 in, -1 squared is positive, so this is a positive. And then -1 minus 3 is a negative. So a positive times a negative is a negative. So I'm definitely going to get a negative answer down here. So that means I know that my graph is somewhere down here and it's approaching this 0 from the bottom. Now, what is it doing on the other side? Is it continuing to go up, or is it just going to touch that 0 and come back down? That's why we have to test another number in this range. So in between 0 and 2, it makes sense to test the number 1. So when I test the number 1, I get 1 squared, which is positive. 1 minus 2 is negative, so I get a negative value. So that means if it's negative, it starts down here, comes up, touches, but it will then come back down since it has to be negative again and go back up to this 0. So let's see what's happening on this side. So let's test the number 3. If we put in a 3 into our function, 3 squared is positive. 3 minus 2 is positive. So positive times positive is positive. So again, negative, touches, negative, crosses through to become positive. And that's going to help us in graphing our graph eventually. If we connect all the points with a smooth, continuous curve, we can do that in a graph, which we'll do on the next page. So first, let's go through all of the things that we've done so far. We've chosen the intervals. So let's break this up into the same intervals we had up above. We know these are zeros. And so the intervals are going to be this interval here, which is between -infinity to 0, this interval, which is between 0 to 2, and this interval, which is between 2 to infinity. Again, the number we chose was -1, 1, and 3. And the value of each of those, it was negative. It turns out it was -3. When we plugged in -1 into the function, we got -3. So f of -1 is -3. F of 1 was equal to -1, and f of 3 was equal to 9. Which means this location is below the x-axis. This -1 obviously is below the x-axis, and this +9 is above the x-axis. So the points on the graph I have are -1, -3, 1, -1, and 3, 9. Not to mention I also have these x-intercepts. My apologies, I didn't have that up there. Okay, so now I'm going to go on to the next page and I'm going to show you how to put this all on a graph. So maybe I'll just scooch that up. And we'll graph at the same time. Okay, so on my graph, I know I have, first of all, I know I have these x-intercepts at 0 and 2. So these points are my x-intercepts. And I also know that I will have these points on my graph. -1, -3. So it starts below the x-axis, comes up, touches this 0, and then comes back down because it has to hit the point 1, -1. Then it comes back up and it crosses through this x-intercept and heads up to 3, 9. So my graph comes up to this 0, touches, goes back down, crosses through, and heads up to infinity. So this would be the graph of this function, which was this one right here. So notice that this graph of x squared times x minus 2 is below the x-axis on both sides of 0. See, it's below on both sides of 0. But the graph touches the x-axis at the 0 of 0, which has a multiplicity of 2. So this 0 right here, which is 0, has a multiplicity of 2. This 0, which is 2, has a multiplicity of 1. So since the graph is below the x-axis for when x is less than 2, but it's above the x-axis for when x is greater than 2, then the graph must cross through the x-axis at 2, which has a multiplicity of 1. So now is when we're going to talk about the multiplicities and what they mean to the graph. By definition, a 0 that has an even multiplicity, so it has a multiplicity of 2 or 4, 6, 8, 10, if the sign does not change from one side to the other, meaning the graph touches. So if I have a 0 over here, that means my graph is going to come up and it's going to touch in reverse direction. In other words, the sign is going to be negative to negative or positive to positive. The sign does not change from one side to the other of the intercept. That's for even multiplicities. However, if the 0 has an odd multiplicity, then the sign does change. So an example would be coming up, hitting that 0, but then it continues on the other side where the sign changes from negative to positive, or it could change from positive to negative. In other words, the graph will cross through. So it does not touch, it actually crosses through and switches to the other side. And there's also such thing as called turning points. Turning points are a point at which it changes direction. If you look at this graph right here, you can see that this graph is increasing, and then at this point right here, it turns and starts to decrease. At this point it turns and it starts to increase, and at this point it turns and starts to decrease. These are what are called the local max and mins of the graph. At each of these points, it is turning direction. If f is a polynomial of a degree n, then f has at most n minus 1 turning points. This polynomial has 3 turning points. But the polynomial of the degree n always has 1 less turning points. So that means the total degree of this polynomial could have at least a degree of 4. Because it's always 1 less than the degree is how many turning points you might have. We might have less turning points, but you might have up to that amount. That would be the maximum number of turning points we could have. So let's explain how this all works together. Here I've got a function, and I want to know how many turning points it has. Well, let's first discuss what the degree of this polynomial is. Here this x has a multiplicity of 1. This x has a multiplicity of 3. So total, the degree is 4. So n minus 1 is 4 minus 1, which is 3. So it could have up to 3 turning points. Now let's talk about end behavior. End behavior is just the ends of the graph. So if I have a graph that's x squared, and it might have other things after it, like plus 3x minus 2. I'm not so concerned with what the rest of this is. I'm just talking about the core power function that is at the very beginning, which is the highest degree possible. Since it's x squared, we know it's going to be a parabola. However, I don't know what the rest of this is going to do to the graph, but I do know the ends of the graph are going to be of an up-up type of situation. Okay, so regardless, no matter what it's doing, inside of here, I know the ends will both be in the upwards direction. Now the graph of negative x squared means it's going to be an x-axis reflection. So the end behavior is going to be down, down. I don't know what's going to happen in the middle, but I do know the ends will be both pointing down. For x to the third, or any odd function for that matter, the end behavior will be down, up. For negative x to the third, we're going to take this and we're going to flip it over the x-axis. So that means my original graph that looks like this will have an up-down pattern. So my end behavior will always look like up, down, regardless what's happening in between. And this will be the case for all even and odd cases. So the end behavior of any even positive function will have the up, up end behavior. For any even if it's x to the 4th, x to the 6th, x to the 12th, it will have an up, up behavior. Any n that is even, but there's a negative out in front, will always have a down, down behavior. Any odd function will have a down, up, and any odd negative function will have an up, down. So we're going to use this end behavior and everything we've learned so far to identify and analyze and graph certain polynomial functions. Let's discuss the end behavior of these four graphs. Which of the following graphs below could possibly be the graph of this function? Well, there's many things we can determine. We can tell the degree of this is going to be 4. Which means it could have up to 3 turning points, but no more. So it will have a maximum of 3 turning points. This graph has 3 turning points, so it could be that one. This graph has 3 turning points, it could be that one. This graph has 5 turning points, so it's not going to be that one because that one has too many turning points. But the graph could also be this one, because it has 3 turning points. So I've eliminated one. What else do we know? We also know the end behavior. Since it has x to the 4th and there is no negative out in front, that means it's an even function with a positive out in front, which means it will have an up-up behavior. This has an up-up behavior, and so does this one. But this one's down, down. So it's not going to be this last one since it doesn't match the end behavior. So now I've eliminated the last one. So the last thing we could do is we could look at possibly the y-intercept. Remember, y-intercepts are always found by setting x equal to 0. So if I set x equal to 0 here, I have 0 plus 0 plus 0 plus 0 minus 6. So y equals negative 6. The y-intercept here is definitely positive. The y-intercept here is definitely negative. So this does not match the y-intercept. It's definitely going to be the second one.